Okay, solving total least squares. What we're trying to solve is this minimization here. And we're going to assume that A is m by n, with m greater than n. So because of that, I probably should have done the indices up here slightly differently. I'm just going to fix those right now, just to be consistent. They're m observations. And we will assume that the rank of A is equal to n. Now, it turns out we can solve this problem even if it's less than that, but this is a little bit more straightforward and it sketches out the solution nicely. In fact, if you go back through carefully, you could work out the other case with the math that we're going to do, but this will just simplify this whole argument here. So this is a situation where we have an overdetermined system, but A is full column rank. Much like what we just used previously as an example of line fitting points. So this would be something that fits that. Okay, let's start with the constraints that we had before, which was y plus delta y is equal to a plus delta a times x. We're going to ignore the error for right now. And we can rewrite this as a plus delta a times x minus y plus delta y is all equal to 0. And we're going to write this in matrix form. We're going to shift around a little bit. The worst part about this, I think, is going to be keeping track of the different terms that we define and use. But this will be a matrix where we have A plus delta A is the left side of this matrix, and the right side will be our column matrix, or column vector y plus delta y, and that's going to multiply our vector y or x, and then our last column will be multiplied by minus 1, and that's going to equal 0. And we're going to now define some terms. So we have c plus capital delta x minus 1 is equal to 0, where c is equal to our A matrix augmented by y, and delta is equal to our delta A matrix, which is the same size as the A matrix, augmented by delta y. Okay, so these are both the same size. This is m by n plus 1. We've added that extra column. Okay, so what do we do now? Well, we have this cool little system where we have C plus delta times x minus 1 is equal to 0. So really, what we're looking for is a delta such that when we add it to C, we get a matrix that's diminished rank. And so it has a vector in the null space. Now this vector is x minus 1. As long as we find any vector in the null space such that the last term is not 0, we can always normalize it to get it of the form x with minus 1. So find delta to create C plus delta with a null space, and then we just normalize some vector in that null space, get x minus 1, and it's in particular the normalization gives us the minus 1 term, and once we have that, we know we have the solution. Okay, so how do we get a delta that will result in a rank deficient C plus delta? That's going to be our next task. So we keep changing the problem, but eventually we're going to get to something that works. Okay. So our original optimization problem now becomes minimize the delta, which is what it was before, subject to rank C plus delta is equal to n. So we'll do some tricks here to try to get that. Let's call this capital X. Then this becomes, since C is already defined, we're minimizing now over X, and delta is just C minus X or X minus C. It doesn't matter because we're taking the squared Frobenius norm. Subject to rank of X is equal to n. So that's the same as before, just using our new notation. And we say that our delta hat is going to be our x hat, the solution to this problem, minus C. So we've already looked at low rank approximation. That's from the previous lecture. And you might think it's a coincidence that we talked about it just at the right time. It's not. So this is a low rank approximation problem. Because remember that C is of rank n+1. Okay, so where is this low rank approximation problem coming in? We are essentially trying to approximate C, and as you recall from before, our C matrix is defined as A augmented with Y. So we're trying to approximate our C matrix, which is now rank n+1, with a matrix of rank n. And we do this by adding some term to it, and we want that term to be minimal. Well, it works out like this. If we add, and in this case really a small term or matrix to C to diminish its rank, we can essentially try delta R UR VR transposed from the SVD of C. And actually, the add was in quotes because we're going to want to subtract that. So our delta would be minus that. So when we added that to our C matrix, we will now have diminished the rank, and it will be the best or the closest diminished rank approximation to C that we can get. And that's where we did that's from our low rank matrix approximation lecture previously. And since we chose delta capital R, this would be sigma capital R, that's the smallest of the singular values, and there we go. So let's just put this all in one place. If C is equal to, and I think I better not use U and V because we've already used that for A. So let's use the terms, the vector W and Z, like this. So if C is equal to W capital gamma, in which case we should probably change this to little gamma, Z transpose, which is equal to the sum n equals 1, n+1. I'm sorry, it looks like I should probably change my notation all the way around to make it more consistent. n+1, n+1, n+1. There we go. Gamma n Wn Z of n transpose. Then we can define x hat as all but the last term, gamma n times W times V and delta hat is just equal to x hat minus C, which is negative gamma n+1 W n+1 and you can see habit is a strong force with me. I should have been a z. So this is a z, n plus 1 transpose. So now we're getting really close to the solution. Remember, we have to unpack all these little definitions we did. So we really want this to find a vector such that the equation c plus delta, we've already got our solution now, times x vector minus 1 is equal to 0. Or in other words, x hat times our x vector here is equal to 0. So we know that this little delta hat matrix we have up above is the one that we want to diminish things. So the null space then is just the span of Zn. So by construction, the null space of x hat is the span of z n plus 1. Because Zn broke everything down into our space into orthogonal. We have orthonormal vectors in Z, and therefore we just need to find a scalar alpha such that x minus 1 is equal to alpha z of n plus 1. Now, it may be the case that we can't. If for some reason the vector zn plus 1 has a 0 in the last space, then this is not possible to do. But otherwise, it is. And it is possible that we don't have a solution. But x total least squares hat vector is equal to minus 1 the n plus 1 term of the n plus 1 vector of our SVD times the whole vector. Let's see, plus 1, 1, up to z, n plus 1, n. Sorry. I actually misspoke. It's only up to term n. Why? It's because we are trying to find that vector there. And the minus 1 term is just there for the normalization. So this is our total least squares solution. To do this, it would be difficult by hand, but it's not that difficult in general. We've defined our C matrix previously right here. We take A, we augment it with Y, we find the singular value decomposition of C. Then we take the very last vector and normalize it by -1 over the last element of the vector, and we take the first n elements, and that's our total least squares solution. Well, what is our delta y and our delta a? Well, we could calculate that if we wanted to, but we don't need to at this point. At this point, we have the solution that we're looking for, which is the x. But if you wanted to calculate delta y and delta a, we could do it from this expression right here, because our delta is equal to delta a augmented with delta y.